Alright, we're going to look at a problem where I think there's two challenges to this exercise. The first is setting up the appropriate integral to revolve this circle around the x-axis. The second challenge is doing the integration, which apparently is going to require some trigonometric substitution. So it's supposedly supposed to make our lives easier, and you'll see how it all works out. Before we do, since we're doing a volume of revolution, we're going to have to take these y values, these y functions, square them. So I'm going to get some of the algebra out of the way right now. Just foiling this requires that we, foil. So the 3 times 3 equals 9, 3 times square root of 4x minus x squared, and then 4 minus x squared square root times 3 gives us that one. And then the square root of 4 minus x squared times the square root of 4 minus x squared is just 4 minus x squared. Collecting like terms yields this result. Similarly, when we square, and I should mention, of course, that this function represents the top half of the circle right here. Purple is going to represent the bottom half of the circle, so that's going to be 3 subtract the semicircle to get that arc down there. So I can foil that in the same way. The only difference is I'm going to get the opposite of 6 times the square root of 4 minus x squared instead of the positive. Now, to set up my integral, I'm going to play a little bit of symmetry games, because normally we would go from -2 all the way to +2, and then integrate the whole semicircle and spin that around the x-axis. But I'm going to double the volume of revolution when I take just the right half of the circle. And so the next bit is the top half of the circle minus the bottom half of the circle. So once again, we're going to take 2 times the volume of revolution, where we have pi r squared minus r squared. So this is the upper circle minus the lower circle. Notice again we're squaring both of those individually and then subtracting the results. That's sort of a shorthand for taking 2 separate integrals and subtracting them at the end. So this is going to make our lives easier. So luckily I pre-foiled, so I just substitute all those values in, and I see the luxury here. We're going to have 13 subtract 13, and we're going to have negative x squared subtract negative x squared, which is those things are all going to subtract out, and we'll just get 6x minus negative 6x for a total of 12 square root of 4 minus x squared dx. So this is a deceptively simple looking integral, but it's going to involve some crazy substitution, so let's get to that piece. This is a trick that I see used quite often, and something that we should get used to. A lot of times IB is kind enough to at least point you in the right direction, and telling you that x equals 2 sine of u. We're going to have to go in faith that this is going to work out for us. So I'm just going to go through the motions. First, I take the derivative of x with respect to u. That's how I get dx is equal to 2 cosine u du. So this dx right here can be transformed into 2 cosine u du. It's a simple substitution there. But I also have to remember to change my boundaries from 0 to 2. First of all, to 0. When x is 0, that means u is 0, because the sine of 0 equals 0. When x is 2, that means sine of u equals 1, which means u equals pi over, well, it says pi over 6, but that's supposed to be pi over 2. I think that'll be changed. Yeah, there it is. So let's go back and, just for my own sake. Don't know why I put pi over 6 there. 2. Yeah. Oh, whatever. I'll just let it be. Anyway, we can now see that, first of all, I changed my boundaries to 0 to pi over 2. And second of all, I replaced x with 2 sine of u. And finally, I replaced the dx with 2 cosine of u du. That's the derivative of x with respect to u. This at first glance looks worse, not better. But there's going to be some nice little identities here to clean everything up for us. First of all, you'll notice that I took the 12 and brought it out with the 2, so you get 24 pi. That's all constant stuff, so we can get rid of it. And second of all, when I square 2 sine of u, I get 4 sine squared of u. Carrying this forward. Oh, well, before I carry it forward, I should point out, I'm having a little trouble here, I'm tired. Yeah, so this is just up top here, I'm just kind of looking at 4 minus 4 sine squared of u. That's actually equal to 4, I factor out the 4, so 4 times the quantity, 1 minus the sine squared of u, which is actually 4 times cosine squared of u. This is a reminder of the old Pythagorean identity. Sine squared plus cosine squared, which I didn't write there, is equal to 1. And if we solve for cosine squared, we get 1 minus the sine squared equals cosine squared. So that's really handy, very important to remember. And that enables me then to express my new integral now as 24 pi, the integral from 0 to 2 pi, square root of 4 cosine of u du times 2 cosine of u du. You might see where this is going. The square root of 4 cosine squared can be square rooted. Then we have 2 cosine of u times 2 cosine of u du, or in other words, 24 pi times 0 to pi over 2 integral of 4 cosine squared u du. Now this, again, deceptively simple. I would love to be able to just integrate this, but the cosine squared presents a problem in as much as I can't reverse the chain rule on this, so I have to be more crafty. So here's another identity that should be handy. That's the double angle identity. The cosine of 2u equals 1 minus 2 cosine squared. That's one of 3 choices in your handbook. When I solve for the cosine squared, I end up with 1 minus cosine of 2u du. Cosine of 2u I can reverse chain rule. Cosine squared I can't. So replacing the cosine squared with all this stuff gives me something that I can integrate, as you can see. Distributing the 4 gives us 2 minus 2 cosine of 2u du. It's a lot of 2's in there. So finally we get to the home stretch. To integrate 2, I just take 2u, because I'm integrating with respect to u. It's important to recognize. So the integral of the constant is 2u, and then the integral of cosine is going to be sine, but I remember I have to reverse chain rule, so I'm going to divide by 2. That cancels out the 2 coefficient. Just to double check, if I took the derivative of the sine, it would be the cosine. If I took the derivative of sine of 2u, it would be 2 cosine of 2u, using the chain rule. So I'm pretty sure I got that right. Now all I have to do is fill in my boundaries. 2 times pi over 2 is pi. Sine of 2 pi over 2 is the sine of pi, which is 0. So we get pi minus 0, or 24 pi squared cubic units. And that checks out. There you go. Thanks for watching.